Hello, my name is Gabriel Nixon, and I am advised under Mr. Stephen Willett and Dr. Sebastian Scherer of the Carnegie Mellon University Air Lab. This summer, I was a 2024 Robotics Institute Summer Scholar, and I was working on the topic of eradicating ambulance deserts, sensor system designed for a new class of unmanned eVTOL aircraft for the GoAero competition. Here's some introduction on this problem. Modern LiDAR and stereo cameras can create 360-degree 3D terrain maps. These terrain maps are used to detect and classify objects. Right now, 4 million Americans live in ambulance deserts, areas of the nation where ambulances take 25 or more minutes to arrive. 4 out of every 5 counties in the nation have at least one ambulance desert. You can look on the map to the right and see the widespread distribution of ambulance deserts across the United States. The GoAero competition was created in order to gather teams to create a large-scale autonomous search and rescue aircraft. If you look at the figure to the right, you are able to see the average human male right next to the dimensions specified in the official rules of an autonomous aircraft for the GoAero competition. This is a 3-year-long competition, and the aircraft must complete courses such as the ones displayed in figure 3 below. On the left, we have a course that tests the speed of aircraft in taking off, doing a lap, landing, loading up payload, and then repeating. On the right, we have a course that shows that aircraft must be able to maneuver quickly over and under barriers and across sharp turns in order to reach an objective. Next, let's talk about our objectives for this research. Our research question this summer was, how can a sensor system be designed to support these autonomous search and rescue flight operations? Our overall design goal was to create a continuous, highly accurate, highly refreshed 3D LiDAR map that minimized sensor blind spots, maximized sensor field of view, and was efficient. Our requirements for autonomous aircraft flight were path planning, collision avoidance, and position estimation. Path planning is analyzing an environment in order to determine the best path of least cost to travel. Collision avoidance is detecting which objects in the terrain map environment are likely to cause a collision with the aircraft. And position estimation is an aircraft using the data, interpreting it in its flight computer, and estimating where the aircraft is relative to the Earth and also relative to its starting and ending points. Our method this summer comprised of core assumptions and prioritization. The core assumptions included low altitude flight. We believe this was a correct core assumption because in the GoAero competition, low altitude flight means more chances for aircraft to encounter dangerous situations. The second core assumption we made this summer was austere environments. Austere environments mean any environments that are unpredictable, dangerous, and possibly catastrophic for autonomous vehicles. This includes, in the real world, places with forest fires, bridges, as well as powerline-ridden zones. Our prioritization this summer was to identify lightweight, commercially available sensor devices and reliable and highly accurate sensors. Let's take a look at this table at the bottom. This table represents the relationship between aircraft responsibilities and pilot tasks. We used this key relationship in order to form sensor requirements for our sensor system. One aircraft responsibility was to have precautionary obstacle avoidance. One pilot task was to guide the aircraft to an area of interest that might have a lot of obstacles. This led us to form a sensor requirement of a high resolution identification of physical barriers in the creation of our terrain map. Another aircraft responsibility was to identify safe landing locations and land autonomously. Our pilot task was to verify a safe landing spot. Therefore, our sensor requirement was to have full field of view coverage below the aircraft underbelly. Let's continue. In our research, we developed some recommendations for our sensor system design. Let's take a look at the left, where we have sensor selections. Our team decided to go with the LiVox mid 360-degree LiDAR, which is represented in the bottom row, because of its capabilities in accuracy, range, and its field of view. If you look at the bottom row and the far left, you're able to see the field of view of the LiDAR mid 360 with a range of 40 meters. The second sensor device we decided to use this summer in our designs was the Stereolabs ZX stereo camera, which is represented in the top row. We decided to go with the stereo camera because apart from the LiDAR map that the LiVox Mid 360 can offer, our ZX stereo camera can offer visual information, including color as well as depth. In addition to this, our ZX stereo camera has a built-in IMU device which can help with position estimation and visual and laser odometry. Moving on to the right, we have used our sensor selections in order to develop a sensor design that we believe is most optimal for our team's competition aircraft. In the top left corner, we have visualized a competition aircraft with 6 rotors. And using this visualization and CAD model, we have been able to place sensors around the aircraft in order to film the images on the right as well as the bottom left. Let's explain. We have decided to use 2 pairs of LiVox mid 360-degree LiDAR and Stereolabs ZX stereo camera combinations because it covers a full 360-degree view around the aircraft. Moving on to the second reason, ZX cameras account for mid 360 degrees field of view blind spots. What does this mean? This means the areas where the mid 360 LiDAR cannot see are covered by ZX cameras, meaning that we will not have any blind spots while we're flying, which is crucial when we're passing underneath bridges or landing or simply avoiding obstacles. Our final point in our sensor design was we have placed our pairs on the top and underbelly of the aircraft to assist with autonomous landing and underpasses. Moving on, we have some conclusions from the research this summer. We have identified some key trade-offs that must be addressed. The first is image zoom and focus capabilities. LiDAR sensors do not offer these abilities. However, the use and incorporation of stereo cameras do. The next is safe autonomous landing. Both the LiDAR and stereo cameras address this concern. The next is the low light level environments and the concern of stereo cameras not being able to record data accurately in low light level environments. LiDAR devices do not rely on external light in order to create their own LiDAR maps. Therefore, the mid 360 should handle this concern. The final key trade-off we have identified was particulate dense environments. These are environments such as smoke, smog, mist, whatever environment has a lot of particles floating around, scattering the LiDAR light, as well as scattering the light received by stereo cameras. In order to address this concern, we have identified that we must incorporate some sort of thermal camera system into our sensor design in the future. Moving on, we have some future work that must be considered in order to develop a full-scale autonomous aircraft with an accurate sensor system that can navigate it safely through austere environments. The first being the weight estimations. Weight is a huge concern for our sensor system because our aircraft must be able to fly and not use large amounts of battery weight. Another thing we've identified for our future work is the effects of aircraft stiffness. Another is the effects of structural deflection. Some more include required system architecture for processing sensor supply data, specific placements of IMU devices along the aircraft, energy calculations for powering sensor devices, and determining the required computational power needed for analyzing collected sensor data. Moving on, I would like to say thank you to Carnegie Mellon University, the Carnegie Mellon University Robotics Institute, Mrs. Rachel Burson, Mrs. Morgan Grimm, and Dr. John Dolan. The references are listed below, and I would like to say thank you for watching my video and learning about my research. Take care.